All right, today we have Michael Lazos from the Torch Compile team, and he's going to talk about Inductor's Cutlass backend and auto-tuning and creating fast kernels and so on. Take it away, Michael.
Oh, thanks, Vic. Today we'll cover these different topics in the talk. First, I'll talk about what Cutlass is and why we're using it. Then I'll talk about TorchInductor's process for auto-tuning different Cutlass gems. And then we'll do a walkthrough code demo of optimizing a Cutlass gem. And then I'll talk about how we can use Epilogue Fusion to further customize the gems to your specific workload, and we'll do an Epilogue Fusion demo. So first off, like what Cutlass is. So Cutlass is a header-only CUDA C++ library. It's heavily templated, so the different gems are kind of or the different choices you can have for gems are template parameters that are known at compile time. And so this kind of allows for flexible types that take into account all the different choices when you're building your different kernel, and you can kind of compose them together. It's also fully open source. This is like as opposed to Cutlass, which is closed source. So you can see exactly what's happening and even make PRs if your exact use case isn't being met. And so these primitives are really performant. A lot of them can approach roofline on really large gems. And the main draw of Cutlass though is enabling auto tuning as a first class use case. And for some problem shapes, like Cutlass kernels can outperform cuBLAS. And this is basically because it's making specific choices for your problem size and workload. And then, as I mentioned before, it also provides customization through Epilogue Fusion. So if ops occur after the matmul, like a pointwise op, like an add or a relu, it will basically take that op and fuse it into the matmul to get even better performance. And so cuBLAS doesn't support that at all. So typically you just have just the matmul with cuBLAS. So now I'll just briefly talk about what auto tuning is. So GPU architectures over the years have become extremely complex with the rise of deep learning and AI use cases. And as the hardware doesn't just like naturally get better every year with transistors getting smaller, there are a lot more choices that are built into GPUs to optimize different gem kernels. And so some of these choices here are like tile size. So that would be like the sub matrix that you're going to multiply when you're doing a matmul. And you can basically pick different tile sizes to align with like the cache size of the specific GPU you're using, and that can get you better performance. And then another kind of choice you can make are is called warp specialization. This is a feature introduced by NVIDIA, which kind of allows finer grain control over groups of threads on the GPU. So before all of the threads on the in a specific warp, which is a group of 32 threads, would have to perform all the same steps. So they'd have to all be doing compute or all be doing a memory read. And now different warps can kind of cooperatively solve a task in the kernel. Like one can be loading memory while another's doing compute. And then similarly, another feature kind of that allows finer grained control of memory and compute is asynchronous memory transfers. So new NVIDIA GPUs like Hopper and Blackwell, this feature called Tensor Memory Accelerator basically allows memory to be read while the compute units are being used. So this can improve performance on some workloads too. And there's also way more choices. These are kind of just a small sample that just to give you the taste of what's possible. Um, and now, like what Inductor does when we're auto tuning is we kind of go with the simplest
Hmm.
algorithm is to just try them all. And ideally, you don't do that because it actually kind of takes forever because there's so many choices that you'll just be compiling forever. So we do have some heuristics to kind of narrow the more performant uh, kernel choices up front. But ideally, you want to just get compile time down so you can try more and more.
Yeah.
Now I'll just show you an example Cutlass kernel. So this kind of just illustrates the number of choices. So this is from the Cutlass repo itself. This is like the default gem implementation. And you can see all of these template parameters. Like these are the element D types, different alignments. You can see the element accumulator you can accumulate in float 32 or B float 16. You can pick the tile size like I was talking about, like thread block shape and warp shape. Those are basically different tile size configurations. And you can also pick the number of stages, which kind of pipelines the computation. So you can be storing some data while some compute units are working and
So
basic. Oh, sorry.
what does it even mean to kind of explore the whole source space in this case, right? Is it like, some of these are Boolean choices, but some of these are like integers or other things. So is there some notion of like a jump between choices when you try?
Yeah, I'd say that the generate script that Cutlass provides, they have basically an API that lets you get the choices. You can specify ranges for these things. But for stages, for example, that's an int, but you're not going to have, some crazy number of stages. There's like a limit architecturally to how many you'll have. So there's kind of known good ranges and Inductor plus there's known good defaults on the Cutlass side and Inductor also we can
Yeah.
tune that ourselves.
So, but what about tile sizes? Or do they like all powers of two or something? What did you
Yeah, they're all powers of two, but we can pad and do different tricks to get it to work. But yeah, and then depending on the number of dimensions and strides in the input, if you want to batch or not, we can apply different tile sizes there. But yeah, so this is kind of just to illustrate the number of choices you have. Go back here. So this is this is just an outline of the auto tuning process. And we've kind of talked about it a little bit. We generate all the choices, and then Inductor will basically pre-compile all of them in separate processes, and then we benchmark them on dummy data, and then we cache the results. So you only basically do this once for your model, and it will automatically apply the auto tuning on all the different matmuls and cache the kernels that it generates for future use. And so all the other nice thing is if you're on a different model and you run this, the shapes will also be cached already as well. So if you have similar shapes in another model, you won't need to like recompile them again. We'll still do the benchmarking phase, but the compilation phase can take a while.
I see. So different models can share the same kind of results, so to speak.
Yeah, and a
Uh,
typical another typical approach here is to have like some sort of remote cache, and which I think we'll eventually try and do, where you can have this um, aggregated bank of all these different shapes and known good kernels for those shapes.
and obviously the benchmarking is happening on the same machine on which you are going to run, or are there some assumptions?
Yeah, today it happens on the machine you're running. Yeah. So we do try to, there's not really anything else happening when we're benchmarking, so it's good to isolate it, but I guess you can't guarantee that. But at least in compile, like nothing else is happening when we're benchmarking. I just went pretty far. Okay, so now I'll just go through the actual demo. Uh, So let's see. Oh yeah, so this is the first example I have. So here, we at the top here, I had you set these two parameters, dynamic equals true, and the D type to just be float 16. Um, Dynamic true will basically just run multiple shapes, and what happens is on the second compile, um, will notice that Torch Compile will notice that some shapes have changed and then compile with dynamic shapes and generate a kernel that'll be agnostic to the shape. And I'll show you how the Cutlass kernel handles that. It's similar to other kernels, how they handle dynamic shapes, but it's kind of hard coded to what the standard for a Cutlass kernel is, showing you different strides and things. And so if you don't enable dynamic shapes in this script, basically we'll just run with one shape and we can actually try both and I'll show the output. And so here I'm just setting up the inputs and then this is basically the setting up the inductor configuration to use the Cutlass backend and limiting the number of choices to two just so we can run in a reasonable time for the demo. But if we go look at the config, um, we can see that the other backends available are A10, Triton, and CPP. And Cutlass isn't on by default today, but we're planning on enabling that eventually. And so, um, yeah, in this example, we just set it to Cutlass so we know that we're using the Cutlass kernel and we can see the output code. Okay, and now I'll just run this, and I pre-cache this so it'll actually run pretty quick. All right, I'll clear my terminal first. So here's the output we get. And I set up, when I ran this, I set torch logs to output code to just print the kernel we generated. Um, and so there's a bunch of just includes at the top, which are different Cutlass dependencies. But generally, like the Cutlass kernel will consist of two things. First, just setting up the appropriate like kernel type. What we kind of saw before, we're setting up all the template types with the correct compile time parameters. And then we'll have like a launcher that launches it with the actual data and sets up the arguments. And so um, this first section here is basically setting up what I talked about, the different types that will represent the mammal. And so here there's two pieces. This is kind of the matmul itself here, and that's the main loop. And you can see that by the suffix main loop here. And so main loop in Cutlass parlance is just the nested loops performing the matmul. And then there's also an epilogue. And so every Cutlass op will have an epilogue, even if it doesn't really do anything. In this case, it'll just be the identity, because the epilogue tells the purpose of writing the result to global memory. And so here you can kind of see, oh, sorry.
Is this where the Epilogue fusion stuff will be plugged in later?
Yeah, when we do the epilogue demo, this will be more complicated.
Yeah. Mhm.
And which is but this kind of just shows like the composability of it in that you
Yeah.
just swap out the epilogue for something else and compile the same thing. And so here's the actual launcher code um, here, and this is where we kind of set up the arguments. And it's kind of crazy. I mean, there's so many nested nested brackets and everything, but this is basically corresponding to the different template parameters, the types or the information they need to run at runtime. And so what I wanted to point out before is here is basically um, the inputs and the outputs. X and W are the input, Y is the output, and
Mhm.
then here are the different size arguments. And
Mhm.
so typically, in like a Triton kernel, you might see like S9 representing different symbols or something. But in this case, we kind of named them to match the naming conventions of a typical Cutlass kernel.
Okay.
And so these are basically used in the launcher code. All we do is just set up the arguments and then check that the arguments are valid for the kernel, and then run them down here. And so this section is the arguments for the epilogue, and this will get larger when we have a more complicated epilogue, and these are just the arguments for the main loop. And this just shows the different strides for pointer A and pointer B, which correspond to X and W.
Mhm.
And then pointer C is typically the bias, but in this case we don't have a bias, so it's set to null pointer. And then pointer D is the output, and so this is showing the strides and the data type of the output. But yeah, so now we can just run it. Well, actually, we already ran it. That's the result right there. So I think this is all I have for the demo, unless you have other questions about it.
Okay. I mean, so I had a high level question. So you mentioned that this is not on by default. So when would you use a Cutlass kernel versus a Triton generated kernel?
Basically, if you think that it could be performant for your backend, so you can just it's not on by default, but you can just add it to the
Hmm.
Cutlass or the Max Autotune backends there and just run it. The main concern today, I think, is compile time. At least this is my opinion, but I plan to improve the compile time over the next couple months with Cutlass 4.
Okay.
Okay, so now I'll continue into Epilogue Fusion. So So in ML models, typically you'll have a gem followed by an activation and some pointwise operations. And so what usually happens is that result of the gem is written back to global memory, and that's kind of shown here. After we do the map model, we'll write the result back to global memory, and then we write it back, or then we read it back in the ReLU kernel to perform the ReLU. So with Fusion, we're basically just taking this ReLU and putting it directly into the main loop of the matmul. And this basically eliminates the read and write, which will give you better performance. The way epilogues are implemented in Cutlass is to basically allow a lot of different, allow a flexible like AST of epilogues, like an abstract syntax tree. And so the idea here is that you can kind of have any tree of operations and represent them using this tree visitor type in C++. And so the way this works here in this example is we're just multiplying A and B and then multiplying by alpha and adding the bias times another scalar and then taking the ReLU. And this is kind of what the tree representation would look like. And we'll actually look at like what the C++ code will look like in the next couple slides. And so the idea here is we just
So
do this.
here,
Oh,
is it just the ReLU that is the epilogue, or are we talking about like a whole chain of kernels that are going to be fused?
oh, it could be a whole sequence of
Yeah.
operations. Yeah,
Okay.
arranged in a tree. Yeah. So this one is more complicated than just the ReLU in the last one, in the last
Okay.
slide. Yeah. Yeah, I thought it wouldn't be as interesting with just a single ReLU here. Um, but yeah, so we'll talk about how we do it in TorchInductor. So the C++ code, writing that by hand can be very tricky because you ended up generating a tree of basically template types with different where they're arguments to each other. And so the way we opted to do this in Inductor was you take your model, we generate Inductor IR from it, and then there's actually a Python tracer provided by the Cutlass team. And so you can basically express your epilogue as a sequence of like Python operations. So you can just do like A times B like plus C. And we generate the Python code for that because that's way simpler to generate than the C++. Inductor can already do that. And we give that Python code to the Cutlass tracer, and that generates the epilogue visitor tree C++, and then we combine that with the Gemm kernel that we're already generating, and we compile that into a shared object, and that's the final kernel that we use. And I'll show all of this in the demo portion too. I can show how we can take the Python expression and compile it. But okay, yeah. So we'll just do the demo right now. Um, so for this, let's have it open. This script is actually just a small script that I wrote to just take EVT Python code and generate the C++, so you can at least see what we're doing.
Oh, so you are writing the trace function that is provided by Cutlass.
Yeah, well, I'm calling into
Yeah,
their
yeah.
thing. Yeah, I guess it isn't that small, but I guess it's like 100 lines, so it's not too bad. But basically, here's kind of a complicated epilogue that we want to compile.
Hmm.
Um, and you can see it's just Python code, and then when I run this, I'll just clear this first. It basically will just generate the C++ code. And so each of these are different constructs in the Epilogue visitor tree API. So here first is an aux load, and that just means we're going to load a value from global memory. So in this case, we have the accumulator that we're loading, which is just the result of the matmul, and we have E, which is just another tensor out there. So we need to use an aux load to load that into shared memory. Um, And then the accumulator is just the accumulator fetch instruction. And then we have the compute, which is just the ReLU. And so we take the ReLU of the accumulator and we can store the result of that because we see that we return Z0 here.
Mm-hmm.
And that's what an aux store does, is it just stores the result.
Ah,
And then EVT0 just gets the result of combining EVT0 compute, which is the ReLU, and combines it with Z0 and Z0. Oh, that's doing the ReLU. I think EVT compute 0. Oh, that's the result of the yeah, of the ReLU of the accumulator. And then here's kind of where the meat of it is happening. So
yeah.
there's more in this case, like we're not actually just a tree, we're actually a DAG. And so this topological visitor gets generated when there you can't represent it in just a tree. So it shows that we take these two compute nodes and use it. It takes basically 1 and 0 here. Does this make sense? Oh yeah, this makes sense. Okay. So 0 and 1 are basically compute 1, its arguments are E and EBT0, and then compute two's arguments are EBT0 and compute 1.
Mm-hmm. Mm-hmm.
And so the result of this entire thing is just the result of this computation, which is representing the result of D here, which is just
Okay.
this
And
expression.
compute one and compute two are just two additions.
Yeah, and you can see those are defined here.
Yeah.
But yeah, so this is how we generate from the Python code to the C++. And then I'll go through an actual example of generating this with, or basically a full end-to-end example of the epilogue. Here this, and then and then while it's running, I'll just kind of go through what we're doing in this.
Okay.
This is very similar to what we did before, except now we added just this ReLU and a multiply after it.
Mm-hmm.
So this will get translated into an EVT. And today the EVT is a little more experimental. I actually have some PRs out to kind of productionize it more. So we need to enable these different configs to use it.
Okay.
So here it's not on by default, so we enable Cutlass Epilogue Fusion, and then Epilogue Fusion is only enabled when the tensor memory acceleration feature is available, and that's kind of what I talked about earlier. It's like an asynchronous memory
Mm-hmm.
transfer,
Mm-hmm.
and so this will filter all of the choices to only include
Yeah.
choices that use TMA.
Mm-hmm.
Um, and then this is today we basically benchmark all of the Cutlass kernels and pick the fastest and then fuse with it.
Yeah.
Um, there's a feature that we use with Triton today where when you actually defer the benchmarking of the choices to when we're doing fusion and try the different choices with the fusion and pick the best choice that's
Mm-hmm.
the best choice to fuse with.
Yeah.
Because it's technically possible that the best choice unfused might not be the best
Yeah.
choice
Makes
when
sense.
fused.
Yeah.
But that we don't support that feature yet with Cutlass, so we disable that. And everything
So
else
just to be
is
clear, then here the auto tuning will happen on the original kernel, and then we'll just add the epilogue after that.
yes, exactly. Yeah, we'll just fuse onto the fastest kernel. And the other setup is kind of the same. We have this dynamic and non-dynamic version.
Yep.
Um, and so we ran it, and this is the result we get. We'll see that the gem is kind of the same, which makes sense 'cause as we discussed, we're just picking the best
Yeah.
kernel there. But the epilogue now will be different because we, instead of just here before it would say linear combination, and now we have EDT compute one.
Hmm.
And this is our tree over here, which represents the ReLU and the multiply. And so here you can see we have the compute one is the multiply and compute zero is the
Yeah.
ReLU, and we just perform those ops. And then down here we can also see that the arguments got more complicated as well. So here we're just providing the information for the aux load. We're telling it that we want to load arg41 and we give the strides of that argument as well. Um, and the interesting part here is now that we use dynamic shapes, we pass the shape values in to the different shape arguments up here.
Hmm.
And we also include, this actually isn't included when we're just doing a regular matmul. We have to include any shapes that are part of the epilogue. The like if we're doing an aux load, we need to be able to provide that shape to the epilogue as well. But actually, it's not used here, so I might need to double check that. But I think um, yeah, it might actually be agnostic to the shape, so I might be able to eliminate the shape arguments for the epilogue. But I'll have to double check that. But either way, we do end up adding the shape arguments there in case they're needed in any of the ops in the epilogue. We could probably do finer grained filtering to
Hmm.
remove those, only use the shape arguments that are used. But yeah, so if I'll just run once with dynamic equals false to just show how when we run this with dynamic equals false, we're just going to have hard-coded shape
Oh
values
yeah,
here.
128, 120, 16. Okay. Yeah, that was the first one.
Yeah. So that's all I have to present today. So unless
Okay.
any other questions.
That's pretty cool. Yeah. So what's before we end, like what's next for this project?
So yeah, the next things are to improve compile time because I think that's
Yeah.
the biggest blocker to putting this on by default. And also when I was talking about um, the benchmark fusion, it's also possible that the compile time might be too slow to make that tenable. Like during every fusion, I don't know if we'll be able to compile
Hmm.
um, every every choice with every fusion.
Okay.
So where Cutlass 4 provides a new DSL that might be able to basically circumvent the C++ compiler and not have to compile C++ and just compile the DSL instead.
So in terms of compile time, is the bottleneck mostly like you're compiling a lot of C++? Is that what it is?
Yeah, yeah, it's just the C++ compiler. Yeah.
Okay.
And
Cool.
dynamic shapes helps with that a little bit because you don't need to basically compile a new kernel for every new shape. But
Okay.
yeah.
Interesting. But in general, dynamically shaped kernels will be slower than static shapes, right?
It depends on the shape. But yeah, the for Cutlass, it's actually pretty close.
Okay.
Because I mean, even in the static shape regime, we're just passing the static shapes to the same arguments. So I actually don't think there's really any like the only drawback you'll get is you're not tuning for that shape. So there might be better choices for that, but I think the kernel like
I
there won't
see.
necessarily be a slowdown, I guess.
I see.
Is
Okay.
yeah.
Okay. All right. This was pretty cool.
Cool.
Uh,
Yeah, thanks for having me.
yeah. See ya. Bye.